A useful device when doing or when considering electrostatic forces is a set of parallel plates. So imagine parallel plates. You can imagine a capacitor, something like that, a large sheet of metal, and then just below it, another large sheet of metal that's running parallel to it, and then the two plates are sitting right on top of each other. And then with your set of parallel plates, you can attach them to something like a battery or something. The reason that this is useful, if I imagine a cross-sectional view of this, is that the electric field that's created between the set of parallel plates becomes constant. This is true as long as the size of the plates, this way, like the length and width are much greater than the separation of the plates. Imagine a charged particle existent in the space between the two plates. It would be, let's make it positive for the sake of argument here, it would be being repelled by the top plate and attracted by the bottom plate. If that charge moved towards the bottom of the plates, they'd be further away from the top plate, but the distance to this bottom plate would be smaller. This change would compensate for each other. So down here, it would get more force from the bottom plate. However, if it was up near the top, it would get more force from the top plate. And in the middle, it would be even. And so what ends up happening is the amount of force changes. This one goes down as the particle goes from top to bottom. This one comes up, but the total of those two things, the part from the top plate and the part from the bottom plate, add up to be constant. So what that means is as that particle moves around between those two plates, the amount of charge or the amount of force it experiences is always the same regardless of its location. That's useful because then we can use the idea of the electric field and work to come up with a relationship between the electric field and the voltage applied across the plates. Keeping in mind that work is equal to force times displacement, but also equal to a change in potential energy. The force, if we're considering electric fields, can be written as the electric field times the charge. D here would be the distance between the two plates, or how much a particle would travel as it went from one plate to the other. And potential energy, again, if we want it in terms of voltage so that we can relate it to the battery that is powering the plates, is voltage times charge. And what we can see is since we have the charge on both sides of the equation, as long as Q doesn't equal 0, we can eliminate it from the equation. And the electric field times the distance between them works out to be the same as the voltage of the battery that is supplying power to the plate. So now we have an easy way to take the geometry and the power source and convert it into electric field, which will predict how much force we can experience. Well, we expect a particle to experience as it's moving between those two plates. So once again, parallel plates are useful because the electric field anywhere in between them is constant. This is because as you move anywhere around here, as the force from one plate goes up, the force on the other plate will go down to compensate, and the overall total between those two things ends up being a constant. And using the fact that we have a constant force, we can use our work formula to relate the force to the amount of potential energy, and as a result, the electric field to the amount of voltage. Since we can control the voltage and the distance between the plates, that gives us a way to create a predictable electric field, and that's really useful if we want to apply a specific electrostatic force to an object.